start. Welcome back, and let me start by thanking the organizers for the invitation. It's a really great pleasure to be here. And so my talk is going to be complementary to Sylvia's talk this morning that you heard. So let me just write a title, but the title, it keeps changing with time. But okay, so I'll write this. Okay, so this is, Sylvia this morning talked about point processes which are in thermal equilibrium and with long range interaction. What I'm going to talk about is point processes, but they are in out of equilibrium, and there is a long range component. It's not interaction, because in non-equilibrium systems we can't talk about energy function. So there will be some kind of long range correlations which I'll discuss, and this long range correlation will actually emerge dynamically. It's a result of the dynamics basically, which will make different degrees of freedom extremely correlated with time, and this will be done by a particular non-equilibrium process which I'll call stochastic resetting, which I'll explain to you as I go along. So this is actually a sort of based on a series of recent works that we did with my two PhD students, Marco Biroli. It's mostly Marco's thesis, and also Gabriele Di Mauro, who has just started, and with collaborations with several people, Gregory being one of the organizers of this school, and also we did some experiment recently with Sergio Siliberto from ENS Lyon, and I'll show you some pictures of that. And on the stochastic resetting part, this is based on earlier work with Martin Evans, which I'll remind you. Okay, so let me just give a brief outline of my talk. So I'll just briefly remind you what Sylvia did this morning very nicely, and just to set up my notations. So this is a point process in thermal equilibrium. So she already told you about the Riesz gas, log gas, etc. I will not repeat all the details, but just to set up the notations. And in particular, I think she explained why these problems are very hard, and that sort of is one of the motivations of these lectures, as we'll see. So this will be very brief, and then I'll give an introduction to stochastic resetting, because that will play a major role in setting up this non-equilibrium point process. So in particular, I'll discuss a very simple model. Diffusion with stochastic resetting. SR will be the acronym for stochastic resetting. So number 3, so after this introduction of a single particle model, then I'll introduce a gas of I'll explain this as I go along, of course. And we'll see that this will give rise to what I was referring to as dynamically emergent correlations between particles. And these correlations will persist all the way up to the stationary state, except that the stationary state is not going to be the Gibbs-Boltzmann state. It will be something else. It will be non-equilibrium stationary state. So usually this is referred to as, with this acronym NES. And what I want to show you then, I'll discuss in some detail that these models, there's a whole class of solvable models. So, despite strong correlations between particles, they share some kind of integrable structure, integrable in a quote-unquote sense. So let me call it solvable structure. In their stationary state, and this this solvable structure turns out to be quite common. It appears in many different problems, and I'll give several examples of that. Including, I'll briefly talk about the experiments. This is a very recent experiment. It's not yet published, and then finally I'll just summary. And there are many open problems because this is a relatively new area, and there are tons of open problems for the young people if you are interested. Okay, so that's sort of the plan. Okay, so let's start. So, in general, this point process that I'm going to talk about, so they can be in any dimension, but for simplicity, I'll just restrict myself to one dimension. So this is, I'm going to first talk about the equilibrium thing. This is just a repeat of Sylvia's lectures, just some, part of it. So the system I have in mind then is just a bunch of points. You can think of them as point particles with coordinates x1, x2, xn. And as Sylvia was saying, so traditionally if you look at the textbooks, usually they are considered in a box, and therefore the the density, average density profile is just a flat profile. But these days there are experiments when people actually, these are colloidal particles, and they usually put these particles in an optical trap, and this optical trap is typically harmonic and is created by lasers. Okay, so they are confined not by a box but by an external potential, and as I said, typically this potential is harmonic. So say something like this, but you can design all other types of potentials also using the optical tweezers. And so normally, when you do statistical mechanics of a bunch of particles, you have the position, but you also have momentum coordinates. But I'm going to assume that these are kind of overdamped particles, so momentum is not a relevant degree of freedom. So momentum coordinates So the configuration of the system is completely specified by the positions of the particles. Okay, so now thermal equilibrium, what does it mean? That means it's sort of connected to a heat bath which has some temperature or inverse temperature beta. This is Sylvia's notation. So this is, physicists like to write this as 1 over kBT, where kB is the Boltzmann constant and T is the temperature. And so now as long as we are interested in stationary properties, I don't have to care about the dynamics. I just need to know what is the stationary measure. And in equilibrium system, the stationary measure, as Sylvia has told you this morning, is completely specified by the Gibbs measure. Okay? So Gibbs measure says that essentially, okay, I'll write a physicist notation here. So it will be different from the probabilist notation. So I'll just write it like this. So this is the PDF of n variables, multivariate PDF if you like. And so I'll use the same notation. So Zn, which depends on the parameters of the system, is a normalization factor, and then you have e to the power minus beta and this energy function. So this is what Sylvia was writing as H. So this is the okay. So the advantage of the Gibbs measure is that, you know, somebody like Gibbs or Boltzmann tells you what is the, so Zn is the normalization constant here. So Zn is just integral this is the partition function. Okay. So therefore, I mean, you know, Gibbs has told us what the stationary measure is, so we don't have to worry about the dynamics here. So only thing that we need to know is what is the energy function, okay? And so this function E, so this function E you can choose, I mean, depending on the model that you want to study. So, but it will have one body term, which is the external potential term. So, for example, V of xi. So this is the one body term because each particle fills the external potential. Then you have the interaction term. Interaction term can be many types. For example, you can have two body interaction. For instance, in the case of Sylvia talking about Riesz gas, this was 1 over xi minus xj to the power s. And you can think of the log gas, whatever these things. And here it's over all pairs, but you can also have a short range interaction, as or you can have even, you know, three body interaction terms. Etc. etc. Okay. So that's the most general energy function that you can write down. And so these are the interaction terms. And this is the guy external potential, which breaks the translational invariance in the system. Okay? So it becomes inhomogeneous gas. Okay? So immediately you see that so the interactions can be either short ranged or long ranged, as was mentioned this morning. Okay, and so what you see immediately, that if you plug it in here in the equilibrium or stationary measure, so first thing that you notice that in the presence of interactions, the stationary measure, the equilibrium measure, it does not factorize, because if you just plug in here, because of this interaction term, if there is no interaction, it will factorize, but otherwise it won't factorize. Okay, so it doesn't have a product measure. You cannot write down this as a product of, you know, n individual IID variables. So no factorization. So the statistical physicists, their job is that, given this, in energy function or Gibbs measure, if you like, you want to calculate, several observables.
Sorry, Satya.
Yeah.
I guess there's a 1/2.
No, it doesn't matter. I mean, you can define your V3, normalize it. Okay. So, so therefore, the observables now. So, what are physicists interested in? Because they are interested in the observables that you can measure experimentally, okay, with your tweezer or whatever, and what we are physicists are interested in. So there are two different aspects. Mathematicians often want to prove that the different, for example, as Sylvia was saying this morning, if the the empirical measure whether it has a finite limit, in going to infinite limit exists, or the unique limit, and so on. But physicists are not so much bothered about such things. I mean, what they say is that, okay, this is a very practical attitude. You give me this energy function, and I want to calculate some object explicitly, which I can measure in the experiments. Okay. So the first observables, and this can be again macroscopic or microscopic. So macroscopic observable, the main observable, this was also mentioned. This is this. So, I mean, this is the average density profile. Again, I'm going to use the physicist notation, but it's exactly the same thing as Sylvia was mentioning this morning. So, I'll define it like this. So, this is empirical measure basically, the expectation value of that, not as a random variable, but the average value of this expectation value. So, because this is something that you can measure experimentally. Okay. So, now this, of course, if you have a just a box, a translational invariant system, this will just be a constant density. But because you have broken the translational invariance by putting it in an external potential, so your density profile typically will be something which is inhomogeneous. Maybe it vanishes somewhere, or it can have either finite support or infinite support, whatever. But it's not a flat density. Okay. So we would like to calculate this object, average density, and if I know in principle, I mean, one thing you notice that if this equilibrium distribution happens to be exchangeable, that means if I make any permutation of any two coordinates, this keeps this invariant. So then this is just a marginal distribution, because to write this you can see immediately. So this average, angle average, means average with respect to this measure here. So therefore, it's just this. Okay. So now you can do this integral. So this means you just, the ith coordinate is x, and all the other guys are integrated over. So this is just the marginal density of the ith variable. And if it is an exchangeable distribution, all the marginals are identical, and therefore, this is just n times that. So this just becomes p marginal. Okay. So that's the average density profile, and you want to know, what is its exact, precise form, and in particular, I mean, in the large n limit, because that's what, typically in the experimental situation you have, even n equal to 8 is pretty large, as we will see. So I want to know what is the sort of average density profile in the large n limit of this gas. So this is a macroscopic object because it gives you a macroscopic shape of your gas, basically. Okay. Now, then I want to talk about microscopic observables. So first thing, and this was also mentioned by Sylvia this morning, this is the order statistics. Okay. So order statistics means that you take your bunch of particles x1, x2, x3, their coordinates, and you just order them such that so which means in my picture here, so this will be M1, the rightmost particle, this will be M2, second rightmost particle, and the leftmost particle will be Mn. Okay, so you just order them, and so this is called the order statistics, and you can ask what is the distribution of the kth maximum, for example, or what's the distribution of the largest rightmost particle. This came up in Kazuma's talk also, because for if you think of these as the eigenvalues of a random matrix, then the distribution of M1 is precisely Gaussian random matrix. It's exactly Tracy-William distribution, which also appears as you saw in the KPZ problem. Okay? So you would like to, so given this equilibrium measure, I would like to know what are the order statistics. Okay, what can I say about the statistics of, so M1, the rightmost particle. So this is usually called the extreme value statistics, or EVS. And in general, for interacting system, it's very hard to solve. I mean, for example, in the case of log gas, where you have this, so for the log gas, as I said, you know, M1, these extreme value statistics, because of strong correlations between particles, so this is actually very complicated. I mean, this is the famous Tracy-William distribution. But in general, they are very hard to compute. Okay? So this is what Sylvia called hard problem. Due to the strong correlations between particles. Oops. All right, so in general they are very hard to compute, and so the simplest example where you can calculate everything, and this will be important for in later lectures. This is when there is no interaction, clearly. So this is what physicists call ideal gas. So this means that the energy function is simply V of xi. So no interaction, and consequently the equilibrium distribution which is so it becomes completely factorized product measure, where assuming this integral exists. Okay, so this is the simplest case, and let me spend some time on it, even though it sort of looks trivial. but it will be useful. So here for this example, all these macroscopic and microscopic observables can be computed exactly, and I want to do it in little detail because later on I will need this. So let's see how it works. So first thing is average density profile. So as I said, average density profile there, you see that the rho of xn is simply marginal distribution of the ith particle. So which means in this notation, this is just P of x. So it's independent of n, and it's just given by this P of x. So you give me the external potential, and then you know that that's exactly the density profile. Okay. So for instance, if you take to be quadratic potential, Px is just a simple Gaussian. Okay. So this is trivial. Okay. Order statistics. So I want to know what is the probability distribution. Again, when I write probability, I mean the PDF actually, and this is I'm using physicist notation. So mk is my random variable. This is the kth rightmost particle from the right. I want to know what is value. What is the probability that it takes the value w, given that there are n such IID random variables. So this is the So let me first write it down and then I'll explain to you. It's quite simple. So okay, so what is the logic here? So you have this, n points, and you are looking at the kth maximum. So this is your mk, which takes this value w. So I forgot here pw. So suppose you put one of them there. So the probability that it takes the value w is p of w. That's this factor, and then I have this is the kth guy from the right. So I have k minus 1 elements to the right, and I have n minus k elements to the left of this guy. So these k minus 1 elements, they have to be all bigger than w, and since they are IID, so it's just px prime dx prime integral w to infinity. And these guys, n minus k guys, they have to be less than w, so therefore it's minus infinity to w to the power n minus k. And then there is a combinatorial factor, because you can exchange them in k minus 1 factorial ways, and this is n minus k factorial ways. So overall you have, so if you fix this guy, then you see that you have n minus 1 guys, and how many ways I can choose n k minus 1. So that is this factorial here. So this explains these two factorial here and n minus 1 factorial. But this kth guy can be any one of these guys. So there is an additional factor n which has to multiply n minus 1 factorial, and that gives n factorial. Okay. So this is fairly simple. So you give me p of x, and this is the answer. Okay. So for instance, if you look at the extreme value statistics, which is k equal to 1, that's because this is the rightmost particle, so it has to take value w, and all the other guys have to be less than w, and there are n ways of choosing this particle. So this is the answer for the extreme value statistics. Now there is a whole literature in statistics mostly statistics and mathematics literature on extreme value statistics of IID variables. So it's a very well studied subject. I'll not go into the details, but one of the questions there is like, given this P of w, this is an exact answer for any n, and now we want to know what are the universality classes, meaning that when I take n to be large, chances are that it may not depend on all the details of P of x, but maybe on the tails of P of x. And so depending on the tails of P of x, you find that these distributions, the scaling distribution of this guy, it belongs to one of the three classes. This is called the classical extreme value statistics classes, Gumbel, Riesz, and Weibull. So this is depending on the tail. If P of x decays faster than any power law, you have a Gumbel distribution, the scaled, centered and scaled distribution. If it has a power law tail, then it will be a Riesz distribution, and otherwise if you have a bounded distribution, then it will be Weibull. But I'll not go into the details of these things. But this is a very well known subject, and you can, there are many books here, but maybe I can refer to our recent book with Gregory. Statistics of extremes and records in random sequences. So this is all discussed in detail there, but I'll not spend too much time on that. But the main point is that you have an explicit formula basically, and after that you can play around with it. Whatever px you have, you can play around with large n, etc., all these things. Okay, but you have an exact formula. So this is the order statistics. Oh, I didn't mention actually two other things, which I'll do now. So other microscopic observables I didn't mention. So that was A, B, and then C, which is the gap statistics. So the gap statistics actually has played a very important role in nuclear physics, because it's the spacing between two eigenvalues, for instance. So this is this famous Wigner's distribution. So gap statistics means that you look at so you have your gas, you have ordered them. So this is your M1, this is Mk, and this is Mk plus 1, and then you have the other guys. Okay. So gap means the distance between two consecutive positions. So this is Mk minus Mk plus 1. Okay. So this is a random variable. It fluctuates from sample to sample, and given the equilibrium measure, what can you say about the gap statistics? And again, in the log gas case, in the case of interaction, it's one, at least for beta equal to 2, one knows the exact answer in terms of freedom determinant and so on. But Wigner actually solved it just for 2 by 2, which is an approximate answer, but 2 by 2 matrices. But it's already a good approximation. It's called the Wigner's surmise and so on. But this is not a very easy quantity to compute. Okay, so this is the gap statistics. So let's see for IID variables. So for IID variables to compute this gap, so since the gap is difference between Mk and Mk plus 1, so you need the joint distribution because if I know this joint distribution, then I just look at the difference between x, k and k plus 1, which is y minus x. I can calculate the gap distribution. Now this object, the 2-point function, that is of the order statistics Mk and just next one k plus 1. So this is, again, you can write down in case of IID variables, when there is a factorization, so let me write down the formula and then you can easily explain. Okay, I'm assuming that x is bigger than 1 by my definition. So this is the x and this is y. Okay. So what's the logic again? So n second phi, you first fix x and y. So the probability that they take the values px, py, and then all the guys to the right of x. So they have to be bigger than x because they are bigger than by definition ordered. So x to infinity to the power k minus 1. All the guys which are left of y, so they have to be less than y, and there are n minus k minus 1 of them because you have fixed 2 guys now. And then you have a usual combinatorial factor n factorial divided by these things. Okay, so you can check the normalization, and one useful check is that if you integrate over y, you get the marginal distribution of mk equal to x. And you can check that it reduces to the above formula there. Okay. So, and once you have that, this joint distribution, so then the gap distribution is so this is just this joint distribution. It's 0 to infinity because it's always positive, the gap. Okay. So you just have to plug in this and work it out, this formula. I mean, again, in general, for arbitrary p of x, it's not so easy to derive an explicit formula, but for some cases, I mean, you can calculate this. And people have again studied this and studied the universality of this with respect to the tails of p of x and so on, but I'll not go into the details of that. And finally, and this was also discussed by Sylvia this morning, we physicists like to call this full counting statistics. Okay. Because this is one object that you can measure very easily in experiments. So what is full counting statistics? Again, I have this my gas of particles. Now you take a fixed interval, let's say minus L to plus L. You can take any interval, but let me focus on this. And let me count just how many particles are there in a given configuration, how many particles are there inside this interval. Okay. So this is just this, I'll write it like this, NL, which is the indicator function. So this indicator function is 1 if a particle belongs to this interval and 0 otherwise. So this is a random variable, and you want to know what is the probability density of this random variable. So this is calligraphic n. I'll just write it like this because I'm very quickly running out of notations. Okay, they are not the same thing. This is a random variable. This is the value. So I want to know what is the full counting statistics. So this is the this is the full distribution. I mean, you can calculate the variance, for example. I mean, as Sylvia was talking this morning, variance, if you find it less than L, for large L, then this is called the hyperuniform. Otherwise, it will be, whatever it is. You can, but it's not just the variance. You can actually, in principle, you can ask for the full distribution of all the moments. And so this object, again, is very easy to compute for IID variables. Why? Because let me first write it down and then you will see it immediately. Okay, so let's see, try to understand this. So I have independent points, right, who are totally IID variables. So I'm asking, how many, what is the probability that the number of them which belongs to this interval? It's like a Poisson process. So suppose that NL of them belongs to that interval. how many ways can that occur is n choose nl. It's a binomial distribution, and the probability of success is just this probability minus L to plus L, because the point has to lie between minus L to plus L. Okay, so this is the success probability, and this is the failure probability to the power n minus nl. That's it. So again, if you know P of x explicitly, you can actually compute in principle this object fully. Okay. And again, I mean, if you, from this you can, very little exercise, you can just work it out the variance, and you will see, because it's a Poisson point process, I mean, it will be just proportional to n essentially. Okay? So you don't be hyper uniform. So for hyper uniformity, of course, you need interactions between the particles. And then the last point I want to make. So what we've seen is that if there are no correlations between particles, that is, if there is no interaction for the equilibrium thermal gas, then they completely decouple, and then we can compute in principle everything once we know what is this P of x, the marginal distribution of each particle. And so the problem is that the moment you have interaction, it makes the problem very hard. And there are two types of interactions, as was already mentioned this morning. I'll call them more explicitly. So this is weakly, I like to call them weakly and strongly so typically when you have a gas with a short range interaction, so for example just nearest neighbor interaction between particles, so I will call them weakly correlated in the sense that typically you will find that if I calculate the connected part of correlation between xi and xj, let's say ordered, it might typically it might decay like with some correlation length, finite correlation length psi, okay, resistance. Okay, so this typically happens, for example, in Ising model on the paramagnetic side. Okay, and so these are the weakly correlated system. That means the system has a finite correlation length psi, and within that correlation length they are strongly correlated, but beyond that they are weakly correlated. Okay, so correlation only is over a finite length scale, and so this is the weakly correlated case, on the other hand, long-ranged interaction. So long-range means like log gas, for example, where everybody is connected to everybody, all-to-all repulsion between pairwise repulsion between particles. So in that case, I would call them strongly correlated, in the sense that this correlation length is typically of the order of system size or bigger. So if you think of these particles, I mean they are almost everybody is very strongly correlated over the full system size, and so these are strongly correlated. Now weakly correlated things, the physicists have a different, I mean they have many different methods to treat weakly correlated random variables, like typically renormalization group. I'll not spend time on that, but if you want to discuss about it, I can discuss separately. Then you have perturbation theory and all other types of methods. So typically there are ways to deal with weakly correlated system. Okay? But strongly correlated, I mean, which is a kind of iconic, but strongly correlated is someone, everybody is very strongly correlated to each other. And so you cannot apply this denomination group method because the correlation length is not finite. So you cannot block this system, because by denomination group I mean very simply, I mean if you have finite correlation length, you have these particles. So let's say you have a typical correlation length psi, then you just divide this system into blocks of correlation length psi. So inside they are strongly correlated, but across the different blocks they are essentially uncorrelated. So you can actually go back to the theory of IID random variables and effectively deal with that if you are interested in various observables. But if the correlation length is infinite, you can't do that. So even all usual methods, these IID things is totally useless. Okay, and so strongly correlated is one of the sort of major problems I would say in dealing with this kind of gas of statistical mechanics, is that how to deal with strongly correlated system. I mean, can we find some methods, models, or how to deal with? And what people do at this stage is that you solve some solvable models. So for example, one solvable model is precisely the beta equal to 2 GUE case in random matrix theory, Gaussian random matrix, which is, as Sylvia mentioned this morning, that this is the determinantal point process, which means that all correlation functions you can write as a determinant of some kernel, and this, because of this particular determinantal structure, you can actually calculate many observables even though they are very strongly correlated. Okay? So DPP is one of the rare exactly solvable so physicists like to call it, this is just a in the quantum field theory, this is a weak rotation or weak properties of this Weak's theorem essentially, which says that higher order correlation functions you can write in terms of the 2-point correlation functions. So this is the status. So I mean basically our point is to find a strongly correlated system for which we can say something, and then number 2 is that so what we want is the following. Okay, so this is my, now I'm going from equilibrium to out of equilibrium system. So I'll tell you what is out of equilibrium a little bit later, but so I want to look at a strongly correlated gas. So this is the goal of my lectures. It's not always guaranteed that system you'll have a non-equilibrium stationary state, but imagine that you have a system with a, and I'll tell you what I mean by non-equilibrium stationary state in a minute. So there are 2 major challenges here. So first is that unlike in equilibrium systems where the stationary measure, because Gibbs has told you, the stationary measure so I'll write it in general like this to distinguish from the P equilibrium. So P stationary measure, if it exists, is not a priori known, right? So Gibbs doesn't exist here. and it is completely decided, fixed, if it exists, decided by the dynamical rules in your system. So here I have to invoke dynamics. It's not, it's not enough to tell, to talk about the energy function here, because you have to really, say what the particles are doing as a function of time and where is it going in the long time limit. Okay? So this is decided by the dynamics itself. And non-equilibrium system means that these dynamics typically violates detailed balance. I'll remind you what this is, or alternatively time reversal symmetry. So what does it mean, detailed balance? So imagine that you have a system with some configuration C, for example the position of the particles. So you think of a configuration space, maybe C1, C2, C3, C4, etc. So you have a configuration space. So typically it's a Markov process in the configuration space. So there are some rates of going from one configuration to another, or the reverse rate, etc. Okay. So you can write down a master equation assuming that it's a Markov process, which says that probability of the system is in configuration C at time t, so del t of that. So what this means is that, so I'm looking at the, the basically incoming and outgoing rate from the configuration C. So it can come from some configuration C prime. This is the rate. This is a continuous time dynamic, Markov dynamic. So this is the rate of coming from configuration C prime to C. So for that, the system has to be in configuration C prime, and then it made this with this rate. It came and added to P of Ct, and you can have a loss term, because if you are at C at time t, then you can go to some other configuration C prime, and you have to sum over all possible configurations C prime to which you can go. Okay? So this is the very general Markov equation, master equation, and so you can write this as so now in the stationary state, if it exists, you have to set it to be the 0, left hand side. Okay? So it should be 0. So the right hand side should be 0 also. So there are two ways you can make the right hand side 0. Either you can say that each term of the square bracket, each of them vanish separately. Okay? So which means this is the long-term limit. So if there is a stationary state, then if this holds, sorry, so that means each of these term on the right hand side in this summation, each of them is separately 0. So this is what is called the detailed balance condition. Okay. The second possibility is that the right hand side is 0, but it's not necessarily that each of the term individually vanishes. So the sum is 0. Okay. So that means detailed balance condition is violated. if the Dittel balance condition is satisfied, if your dynamics, you give me these WCs and I can check whether this satisfies this condition. Okay, I'm not telling you the exact details of how to check, but if you find that it satisfies the Dittel balance condition, so these are the systems which we'll call in equilibrium systems. And in fact, for such systems, given this Dittel balance condition, you can actually construct an energy function, effective energy function, and you can write the stationary state as e to the power minus beta into energy of that configuration. And this energy function you can construct out of these rates. So rates are fundamental objects here, not the energy function. Energy function, the unique energy function you can construct out of these rates. And so we'll call these as equilibrium systems. Whereas if this is true, that Dittel balance is violated, then this will be called non-equilibrium stationary state or non-equilibrium steady state. So what this means, again in the configuration space, this condition violated means that there are the currents, non-zero currents in the configuration space, probability currents, and so therefore, it's a overall, the probability of a configuration is not changing in time; it's stationary, but there is also non-zero currents flowing around in the configuration space, and that's what makes it a non-equilibrium system. Okay. So that's the general definition, and in general, when the Dittel balance is violated, to determine the stationary state, this is a very difficult problem in general. So there is no Mr. Gibbs which tells us what is the thing, and so you give me the W's, and I want to calculate the stationary state if it exists, and it doesn't satisfy Dittel balance. In general, to construct this explicitly, the stationary configuration, stationary state, is very hard problem. Okay, so this is the major problem in non-equilibrium statistical physics. Okay, and the second thing, so this is the first thing, that is first problem, two major challenges I said. So what's the second challenge? The second challenge is that imagine by some means, by hook or by crook, you know this. By some clever things, you manage to calculate the stationary state. But then typically this stationary state again will not have, I'll give you examples, will typically not factorize into product measure, into product states. So therefore computing any observable, observable by observable, I mean these four observables I mentioned, the average density profile, which is macroscopic, and the microscopic ones like gap or order statistics, where you go with a microscope and you just look in the zoom in and look in details in the gas. So computing observables both macro and micro are also very hard. Okay. So there is a two-level problem. First, to determine the stationary state, and the second thing is that knowing the stationary state, how to compute these observables. Okay, so this is the sort of major two challenges. So in the rest half an hour, so what is our goal then? Finally, what I want to do. I mean, this is how we came into this business. So the goal, our goal, was to search for generically interacting particle systems typically many body, of course. With the three properties. So what are the three properties? Number one, it converges at long times to Ns, which means dynamics violates detailed balance. Number two, in the Ness, the particles are strongly correlated, because that was our basic motivation to study, strongly correlated system where there is no simple physics methods. So equivalently, this would mean, so here I prefer to call it long range correlation, because it's not really interaction, because there is no energy function here. Okay? So long range correlation. So that means everybody is, correlated with everybody else, just like in the log gas or Riesz gas, but there it was equilibrium in the energy function. But here somehow your structure of the stationary state is such that there is very strong long range correlation between these particles. Everybody is connected to everybody. And then three is, despite the presence of strong correlations, they are exactly solvable. By exactly solvable, I mean explicitly solvable for all these different observables. Okay. So, and what I want to show in the rest of the lectures is there's a whole class of models. Actually, these models can be in higher dimension also, but I mean, as I said, for simplicity, I'll stick to one dimension. Yeah. Sorry. Yeah. No, you don't need to actually, because you can, for example, I mean, when people study overdamped dynamics of a Brownian particle, you will see an example, explicit example later. I mean, if you, drive it by putting a heat current or something, there are many ways to drive a system out of equilibrium. So it can be overdamped dynamics, basically. It doesn't have to be always momentum dynamics.
So Satya, this is, the model is these criteria purely theoretical, right? But usually there's some empirical connection there.
I wrote there, there's an experiment also, we'll see.
But one could have a model that satisfies these, but also is not real.
Yeah, but even if you cook up with that, that's already something, because because these are very difficult problems, and we want to make progress. I mean, not necessarily, you don't have to always, you can be a physicist, but that doesn't mean that you have to always work on systems that the experimentalists are doing, right? So you can, I mean, sometimes theory can guide the experiments. So. And and this is actually inspired, you will see in a minute, this is inspired by what I mean by stochastic resetting. So I have about 25 minutes or something, right? Okay, so can I use the slides, please? Yeah. Oops. So I want to use this slide just to show you some pictures of. Okay, so what is stochastic resetting? So stochastic resetting is this sort of relatively new area in statistical physics, about 12, 13 years old. But in the last few years, last decade or something, it has seen a lot of developments, both theoretically and experimentally. And also it has gone out of statistical physics. It's been now applied to search processes and computer science problems and many other problems for the reasons that you will see in a minute. And so it's a very interdisciplinary subject in some sense. And so we started working on it a few years back with Martin Evans. And and you will see that even this problem that I'm talking today, it will be heavily inspired by stochastic resetting. All right, so what is stochastic resetting and what do we care? So imagine that you have a growing, the first motivation comes from population dynamics. Imagine that you have a growing population. So this is a picture that you see of New York City, Manhattan. So this is 1609. It was just a point here, and then it sort of grows, is growing with time, okay, and typically exponentially growing. Okay. So the population of its either the size or the the number of people in a city, it typically grows with time. And similarly, you can do a control experiments in a lab. You can grow bacteria on a petri dish. So you start with the bacteria, these 3 bacteria, and then they grow, they multiply, and they grow typically exponentially, okay, very quickly. And so you can do controlled experiments here. You can measure the population density and so on and see how it grows with time. Okay. But obviously, it cannot grow indefinitely, because otherwise, everything will explode, right? So there must be some other events which will stop this growth, and these are extreme events, okay, which are like earthquake, tsunami, or whatever you want. COVID, etc., pandemic. So these are rare events. They don't happen every day, but if they happen, their effects can be quite devastating. And so, for example, it can wipe out the population of a city, and then so you can do anything. And so, for instance, if you look at the population size of a city as a function of time, you see the typical population is growing exponentially, and then some catastrophic event happens, like I don't know, earthquake or something, and then suddenly the population size gets reset, because either people die or they leave the city for whatever reason. It goes down. Okay, it doesn't go down to always to 0, but it doesn't have to be exactly go down to 0. It can reset to any value basically of order 1. And then again with time, slowly the population again grows with time, and so on and so forth. Okay, so this is there is this population growth, and which is interrupted by this catastrophic reset process. Okay, so this reset is also stochastic because it happens at random times. It's not a periodic reset or something. It can happen at any random time. Typically, these are exponentially distributed, the intervals between successive resetting. Okay, so there is a competing effect of growth and reset. Okay, and actually, this is very important in this in the context of bacterial growth, because one of the main source of death in the hospitals across the world is actually the drug-resistant bacteria, basically antibiotic-resistant bacteria, and that typically happens because when people often, in France it particularly happens because people often tend to take too many antibiotics. Okay, so when you take too many antibiotics, what happens? You can think of this experiment. So you grow, your bacteria is growing, and then you put an antibiotic, and when you put the antibiotic, it kills most of the bacteria. But 1 or 2 of them might survive, okay, and then they mutate, they change, and then they start growing again. And so again, if you put antibiotic, again they'll kill some fraction of it, and again it will grow. And so you can ask that does it stabilize this population at long time? Okay, if I randomly keep antibiotic put antibiotics without any this thing, so this actually, you will see that it actually stabilizes the population. So that's the reason why these drug resistant bacteria are rampant in all hospitals, all over the world. And so the question is that will the population size stabilize at long times? Okay, so that means, is there a stationary state at long times? Okay, So this is the question that people ask in this population dynamics literature, and so this is it's an effect of stochastic resetting, you see. The second motivation actually comes from search processes. So as you know, search processes are ubiquitous in nature. I mean, animals searching for food, or for example, helicopters searching for a survivor after a shipwreck, or even protein searching for a site to bind on a DNA, or even more mundane example like I mean, if you are debugging your computer program, you are looking for the bug in your computer program, and so in many of these search problems, it's quite natural intuition tells us that if you have searched for a while and you haven't found it, your bug or your whatever food or something, then maybe you should give up and go for a coffee and restart the whole process from the beginning. Okay, because the rationale is that if you restart, you might find a different pathway to arrive at your target. Okay, which you would have probably not spent a lot of time in searching in vain. Okay, and so this is the sort of the idea behind search process, that sometimes people empirically have seen that typically what you do, you search for a while and then you go back, okay, and you restart the search from usually from the starting point, but from some other any other point. So an example is here. So imagine that this is the visual search. Okay, so imagine that you have a crowd and you are searching for some friend's face in the crowd. Okay, so how do our eyes search? Okay, our eyes never scan from one side to another side. Okay, so what it does, it starts from some point here, it does a diffusion, local search, doesn't find, then typically comes back and again restarts the search somewhere else. So in fact, I mean, people do experiments. So this is the psychologists, they do this experiment. So they they show these letters, the board, huge board, to a patient, and this patient, they put a microscope and a camera in the eye, and they ask this patient to look for, there's only one letter B in this milieu of P, and they ask the patient to look for the letter B, and they see how the eye moves. Okay, so the camera actually tracks the eye things, and again, you don't scan from one end to another end. You just start from some point, search locally. In fact, this is schematically, you can see this is the trajectory. So you start from this point, you do a random walk, and don't find, you come back to O, and then you restart. Oops, sorry. Then you restart and you go, the process searches somewhere there, comes back locally, and so on. Okay, and in case you haven't found the B, it's this okay. So, and the other problem is actually very, it's a problem of much current interest in the context of machine learning and so on. So in fact, I mean, typically people are looking for the global minimum in a high dimensional landscape. So imagine that you have a high dimensional landscape. It could be, it represents the height of this surface, represents the energy of a configuration, maybe in a glassy system or something like that. And so you start from a given configuration, and typically in this kind of algorithms like simulated annealing, so you make a local move by flipping a spin or by moving a particle. So you move from one configuration to another configuration. But the problem is that, I mean, at low temperature, for example, typically you might actually get stuck in a local minimum for a very, very long time. Your goal is to find the global minimum. Okay? But then you will spend all your time here, and you keep on searching, don't. So what people do empirically, and this is done in all machine learning algorithms, is that you typically go back and you restart the search typically from the initial configuration, but it could be any other configuration here, and restart the search. And again, the rationale is that when you restart, you might find a different pathway, and you might arrive at the global minimum much faster. Okay? So search processes actually get expedited by this resetting process. That was the sort of general wisdom, which was which is this question basically. That so this was people have been using it empirically, and what we wanted to know is that quantitatively, does it really reduce the mean search time of a target? If you introduce this kind of stochastic resetting, okay, does it help really? And the second thing is that okay, so there are two issues then with stochastic resetting. That so you have a system which is evolving under its own natural dynamics, which can be anything, and then you switch on this resetting once in a while. And does the system reach a stationary state at long time? And does stochastic resetting make a random search process efficient? So these were the two questions that we were interested originally, and this is actually So as usual, I mean, Boltzmann was always a pioneer, so he always says nothing is more practical than a good theory. So we want to have, have a good theory for this. So with Martin Evans, we actually came up with a very, very simple model, which is this diffusion with stochastic resetting. And this will be the sort of cornerstone of what I discussed today. And this will serve as a basic building block. So I want to tell you about this model, and maybe I can go back. How much time? Okay, this is not too much time left, so I can just tell you. It's very simple actually. Okay, so maybe I can use this bit here. All right. So what is the model? So a model is just, you have a single diffusing particle, let's say in one dimension for simplicity again, and it starts at the origin, and it's just moving just according to Brownian motion, and then from time to time at random times you reset, okay, and the intervals between successive reset is drawn exponentially. These are independent, it's just a Poissonian resetting, so they are drawn from an exponential distribution with rate r. So the dynamics is the following. So I look at the position of the particle at time t. So and then I update it by, it's a continuous time dynamics. I update it. I go back to 0. This is the reset move with probability r delta t in a small time dt. And with the complementary probability 1 minus r dt, I do diffusion. That means I just add a Gaussian white noise to it. And I'm going to use Kazumash's notation here. And normally this is the dBt, and in mathematics notation. Okay, so physicists like to use this kind of notation. So d is the diffusion constant, and this is just a Gaussian white noise. So that's it. That's the model. So r is the only thing. So when r is 0, it's just ordinary diffusion. You do this resetting, and you ask what happens to this particle, okay, position distribution. So the question you want to ask the following. So I want to know what is the probability density of the particle to be at x at time t, starting from initially at the origin. Okay? So this is a Dirac delta at the origin. So if I did not have any resetting, if resetting rate r was 0, so this is simply just Gaussian diffusion. And you ask, okay, if I now introduce the resetting, so what happens? Okay? How do I calculate this PR of xt? So the answer is very simple. So maybe I can just do it here. So first you can write down a Fokker-Planck equation. So PR of xt. So once again I'll write down a master equation of Fokker-Planck equation. So there will be d. So this is just the usual diffusion term. So xt. And then I'll have a loss term, which tells me that if I am at x with rate r, I'm going away from to another position to the origin basically by resetting. So therefore this is a loss term for at x. And then I'll have a gain term, but the gain term will be there only if I happen to be at the origin, because I can gain by resetting from other sides if I happen to be at the origin with rate r. And then here you will have put PR of x prime t dx prime. So this tells me that I was at x prime, okay, and with rate r I reset to x, and therefore this contributes only if I happen to be at x. And this is the master equation. There is nothing else. So when r is 0, of course you will get back the usual diffusion heat equation. Okay, and but one simplicity that happens here is that by normalization, this guy is always 1, right? Because this probability density is always normalized, so it's 1. So you don't have this term. So you just have this. So it's just a source term here, r delta x, and you have this initial condition, which is this guy. Okay? So first thing you notice that this resetting violates the detail balance, right? Because you can go by resetting to the origin, but there is no reverse move. So you can check yourself that it definitely violates detail balance. So if there is a stationary state, it has to be a non-equilibrium stationary state. There will be probability currents. But then without this source term, this is actually quite trivial to solve, because this is 1 by normalization. So just define the Fourier transform. So then the Fourier component satisfies a simple, first order equation, which is that's it, and this you can trivially solve. So the solution is, and you have to solve it with the initial condition, which in the Fourier space at t equal to 0 is just 1, because this is the delta function initial condition. So this is trivially okay. You can check that this is the solution of this equation. All right. So we have this solution, and you can actually invert the Fourier transform trivially, right? Because the Fourier transform, we know that the Fourier transform of inversion of e to the power minus dk square t is just the Gaussian propagator itself. Okay. So I can do the Fourier inversion here, and I can do the Fourier inversion here, and then I can write this in this way, okay, where P0 is just the propagator itself, free propagator. Okay. But this has a very nice renewal interpretation, which I want to tell you, because this will be useful later when I go to multi-particle case. So what is the interpretation, physical interpretation of this variable tau here? You see, I mean, if I look at this guy here, so I'm looking at x at time t. I want to know that the particle is at x at time t. So what is the first term? So first imagine that you had no resetting event at all. So that means this guy goes freely from 0 to x. So the probability that there is no resetting in time t is just e to the power minus RT, and then you have a free propagator during that time, which is just a Gaussian propagator. So that's the first term, which corresponds to no resettings. But then you can have one or more resettings. In that case, all I need to keep track of is the time since the last resetting, because I don't care what happened before, because I know that if this is the last resetting, that means it has come to the origin, and after that it has no resetting, so after that it's a free propagation. So P0x tau is a free propagation. So tau here is the time since the last resetting. So that means if I so this is useful to remember. So I have this this resetting, etc., etc., and this is the last resetting. So suppose this is the t last, which itself is a random variable, and I'm looking at a time t, and this is my tau. So tau is t minus t last. So if I know tau, okay, then I'm done, because after that it's just the x dependent part is just a free propagator during tau. Now what is the probability that the last resetting occurs tau time backwards of t? This is very simple, because you want a point to occur here, a reset to occur here, which happens with probability r d tau, and there is no reset in this interval. This is a Poisson process, so it's just e to the power minus r tau. Okay? But then this tau can be anything from 0 to t, so you have to integrate over 0 to t, and that's it. So that's the meaning, physical meaning of this thing, that you have a tau here, whose physical meaning is that it's the time since the last resetting. Okay? So this renewal interpretation is actually very important, and then you immediately see that as t goes to infinity, then this term just drops out, and you just have 0 to infinity, and this integral you can do easily, and it just becomes a double exponential. Okay? So the length scale here is square root of d over r, which means this is the typical distance that the particle moves between two successive resettings. Okay? So mean free path, if you like. So this is a double exponential distribution, and so this is very nice. So first of all, I mean, this is a, as I said, this is a non-equilibrium stationary state because detail balance, as you saw, is manifestly violated because of the resetting move. So it has a current in the probability current in the configuration space because particles are always going back to the origin by resetting. So there's a non-zero current, even though the probability distribution, position distribution becomes independent of time. And even though, and this is an important point, that even though it has a kind of Gibbs form with an effective potential which is mod x, this is not really equilibrium problem. In fact, this potential is effectively dynamically generated because you are resetting all the time. So effectively, it's like creating a dynamic effective potential, and the stationary state is given by this. So this was the first prediction, that there's a stationary state which is non-Gaussian and non-trivial. And then this was very recently, about 5 years back. I mean, there was a group from Tel Aviv. So they did the experiment with an optical trap with colloidal particles, and you can see that the experiment and theory matches perfectly well. And so this is the stationary state of a single particle using holographic optical tweezers. Okay? And so since I don't have time today, so what I'll do is I don't know if I probably will not talk about the mean first passage time, because that's another prediction, that there are two issues I said. One is the stationary state, and the other is the first passage thing. Does resetting really help the first passage time, reduce the first passage time? And the answer is yes, it does, but I'll not go to that because this is a target search. If I have time later, I'll tell you. I'll just skip this part. So basically, from this simple toy model, what we learn is that one is that there is a non-equilibrium stationary state, and there is an also optimal resetting rate, which I did not show you. There is an optimal resetting rate R star, which makes the diffusive search process efficient. Okay, so I didn't talk about that today. Okay, so this toy model actually, as I said, led to an explosion of activities in the last decades. There is a very long list of problems in which people have, it's from ecology, animal movements, and navigations, and so on. There are some reviews available with Gregory and Martin Evans. We wrote a review in JPhysics where you can have many of them. There are many reviews by now actually. And so in a nutshell, so you see one thing you realize that stochastic resetting is actually a very general concept. I mean, I use diffusion as a simple model, but you can think of any dynamics, whatever is your favorite dynamics. You can take a many body system, you can take a single body system, whatever it is. Its dynamics could be any deterministic, stochastic, classical, quantum, whatever you want. Okay. So the main algorithm is that you evolve this with its natural dynamics up to a random time, and these random times are statistically independent, and they are drawn from whatever you can choose your p of tau as you like. But the simplest choice is the Poissonian resetting, which is just r e to the power minus r tau with the rate r. And it's a renewal process effectively. So essentially, you evolve the system is the natural dynamics up to random time, and then go back, and then again evolve random time and go back, and so on. And the question is that not question. I mean, it so happens that typically this drives the system into a non-equilibrium stationary state, and we want to characterize such non-equilibrium stationary states. And what I want to show you is that in the next lecture is that now we'll go beyond one single particle. We'll go to n particles. And we'll see what stochastic resetting does, and you will see that these three things that I mentioned here, namely that it will converge to a long time to a non-equilibrium stationary state, and in this nest the particles will be strongly correlated, long range correlation, that makes the connection to the Sylvia's talk. I mean, this whole subject of this course. And what we'll also see that despite the presence of strong correlations, that these models in the stationary state, they are explicitly solvable for all the observables that I mentioned. So these are very sort of nice examples of strongly correlated systems where despite strong correlations you can calculate many observables exactly. Okay, so I think I'll stop there.
Any questions? If you're in a bounded domain, is it better to reset to the origin or to
Okay, so this is a good question. Actually, bounded domain, there is a phase transition. it turns out that there's a two length scales here, square root of d over r, which is the typical distance the particle travels between resettings, and your system size L. Okay, so there is a critical value. It turns out if you take the ratio L over square root of d over r, there is a critical value. If it is close, if L is small, then you should not reset. Okay, and if L is large, you should reset.
Well, I guess I'm thinking you could reset to the origin, or you could reset. Like
no, in general, you can reset to any arbitrary point. You can draw from a distribution. So you can, people have studied all kinds of variants of this model.
And is it still non-equilibrium? I'm just thinking if you reset uniformly in space, how could you have a current?
Well, I mean, in the sense that this is a your reset distribution is quenched. In the sense that you say that okay, every time you reset, you choose the position from a given distribution. Okay, once you have that, then it violates little balance basically. Sorry, can you speak it a little bit loud? No, I have not had time. Next lecture. So today I just this was just a prelude. I mean, just one particle problem, and then we want to see what happens for many particle problems.
So imagine you're looking for something like value of RAM or whatever, but still it's very close. You're not so fast, so maybe you may depend slightly on the position or something like that.
Yes. No, in fact, I mean the optimal reset. I didn't have time to talk about the if you want, I can next lecture I can talk about the first passage properties. The optimal resetting rate actually does depend on the initial position x naught. Okay, so for instance, I mean, right. So you see that for a 1D problem, if you calculate the mean first passage time. So x naught is the distance from the target basically. Okay, so this is the mean first passage time as a function of the resetting rate r, and what you see is that it diverges when r goes to 0, it diverges when r goes to infinity. It diverges r goes to 0 because if you don't have any resetting, just a Brownian diffusion in one dimension, in the first passage time distribution decays as a power law as 1 over t to the power 3 by 2. So the first moment of that is infinite. That means you have a trajectory which is taking you far away. Maybe, yeah. I mean, this
when you have a very long code.
Yeah, very long, exactly. Very long code, precisely. Yeah, you just get lost completely. So it diverges at this side because of such bad trajectories, taking you to the opposite side of the target. Whereas, on the other hand, if r is very large, you're all the time resetting to your initial position, right? So you get localized completely into this, and again you miss the target. So it diverges at both ends, and there is an optimal resetting rate r star, which does depend on the initial position, of course, I mean, from the target. But, and this is in fact explicitly given by this formula here. R star is given by as 1 over x naught square with some gamma which depends on this. Okay. So, but the point is that, you might actually, some people always ask this, that, that x naught, if I already know, if I don't know the distance, x naught, then how can I calculate the point is that, it's an important point, but the point is that it's many problems. What you have an idea of where the target is. Okay. So for example, I tell you, let's say in 2 dimensions we are here. Okay. I tell you that okay, the canteen is 1 kilometer away. Okay. But I don't tell you the direction. Okay. So then you can search anywhere. You will spend enormous amount of time. But here resetting is helpful. Even though you might know the distance, roughly it's 1 kilometer, but you don't know what the direction is. So as the dimension increases, it actually gets better and better. Resetting is better and better as the higher dimensions. So, so sometimes you may have the idea of that the target is 15 kilometers away, but you don't know the direction. Okay. So in that case, resetting is the very good strategy actually for search. Yeah.
Thank you very much. So if there's no more question, well, thanks again to all the speakers.